Yep.
So we have to wait. Ja, das ist wieder online.
Wie viel ist es denn?
Weißt du, wie entspannen ein Nachnamen heißt?
Gute Frage.
Ich kann das ja dir überlassen, die alle vorzulesen. Ne? Die anderen kann ich alle aussprechen. Delinio Labo.
Probably not too far off. Yeah.
On real-world protocols. The first talk is on key schedule security for the TLS 1.3 standard by Chris Brusca, Antoine Delignon-Levaux, sorry for butchering that, Christoph Egger, Cedric Fournet, Konrad Kobruck, and Mark-Ulf Kohlweis. And Christoph will give the talk.
Okay. So I'm going to talk about TLS key schedule security. And so first note, maybe for me, this project was a lot about figuring out how to work with complex protocols and how to build like modular proofs that allow us to handle this kind of protocol. If you miss some key exchange-ish introduction, there's also a very nice 5-minute introductory talk by Chris that is online, so you can also check this out. Perfect. That's actually working. At the very start, so maybe first revisit key exchange. Key exchange is just a protocol where two parties exchange messages, and in the end, they both derive some sort of symmetric key. And this can then, for example, be used to create a secure channel, which allows the two parties to securely communicate. And key exchange protocols may even derive more than one key. They can come up with quite a lot of keys. And one of the ideas, why would you do that? Well, one is that you can have different uses. So you can have a second channel for the other direction, or you can export these keys for external use and then be sure this concrete instance of a symmetric key will not be confused with one that can be used for a secure channel establishment. So can be useful to have many keys. Now the question is, if you have many keys, how do you end up at having many keys? And okay, yeah. Note that I missed. We're looking at protocols and we want to have many executions in parallel. So we also, of course, have some sessions, some interactions in this key exchange where the adversary plays one of the roles. So some of these keys will be known to the adversaries and some will not. And I think this is kind of somewhat important to keep in mind that some of the keys that we produce in this protocol will be known to the adversary. And we only want guarantees for the other keys. So this is where I was going to. So how do you end up having many keys? And this is essentially the key schedule. And as you see at this example for TLS, this can be quite a complicated cryptographic primitive in its own. All the lower keys are actually, clicker. So all these keys here are actually keys that are exported by TLS. Given that this is somewhat complicated in its own, it might be a good question to think about, can I reason about this primitive in its own right? And then end up with something like this, where I start from having a protocol. And instead of analyzing this protocol as a whole thing, I split this up and I have a part that only considers itself about message flows and all that kind of thing. And a second part that models the key schedule and its security properties. And this is what we are trying to do in this work. And then you get a very nice modular proof. So you have a first part here that talks about how this key schedule helps us to reach key exchange security. And you have a other part that argues security of the key schedule. And we do have a lot more structure in this as well. Before we go into the details of how you prove such a thing, let's take a look at the model. And here this is to explain how this description works. There are packages here. Packages are just like objects that contain code. So a package has like methods that you can call on it. And we call them oracles. And the arrows are just oracle cores. So the adversary here calls an extract oracle on this extract package, which does then some operations. And here you find also the oracle names. So in a way, this is just like a call graph that you would expect from object-oriented programming. And it also neatly fits into this design of code-based proofs. So we have like for all of these elements on the slide, we do have code-based description. It's just split up into manageable parts. And then we can talk about these parts individually. So the first part here that we have that has this check thing, while we try to look at a key schedule in isolation, we do want to import some security properties from the key exchange. And here this check just disallows the adversary on the left to make some interaction with the key schedule that it wouldn't be able to do in a key exchange protocol, and that we need to prove properties. And I will come back to that in a bit. Then we have the part that actually computes the key schedule. And if you remember the picture that we had, here we have like this expand and extract functions, which are standard key derivation functions. And we have for them, we have here an extract and expand. And we also do have Diffie-Hellman over here because we do model properties of Diffie-Hellman. And finally, we have what is called game here. Game is taking care of both storing information and for modeling security properties. And security properties, I mean, I probably don't need to explain this to you, but you usually have game-based security definitions. So you have a real game, and you compare this with an idealized version of this game. And then you claim or you require that they are computationally indistinguishable for an adversary. We allow ourselves a bit more freedom in this work and do simulation-based security. So we don't require that the protocol in the real and the ideal version are exactly the same. But we just demand the existence of such a simulator and then have the security properties and the functionality. And let's talk about the security properties that we are looking at. So there's the adversary here that's interacting with this get method or get oracle on this package. And this is for retrieving output keys. If you're familiar with key exchange, you usually have something like a test query that gives you the produced output key. And this is kind of similar. So, and what do we want? First thing, we want that these keys are pseudo-random. And of course, as I said, like we only want them to be pseudo-random for keys that are supposed to be like inaccessible to the adversary. So this is exactly what we require here. So if the key was honest, we don't store the key as produced by this key schedule protocol, but we just store a pseudo-random string. And then the adversary needs to distinguish. Second property we want is model in this log part here. And here we require that keys produced by different execution traces through this key schedule will not end up at the same value. So this H here is a handle, and we come to that also in a second. And it just models the execution trace. So how do I arrive at this key in the end? And there should not be two identical keys derived in on different paths. So this is the security properties that we have and that we model in this book. Now this game here is a big package. In fact, for the first proof step that I'm showing in a minute, it's way more convenient to have it split up. And we have key and logs combinations for different types of keys. So we have input keys up here, like intermediate keys here and output keys. And then we can, in game steps, change properties or like requirements we have on these keys until we arrive at the ideal security game. And it's actually even a bit more complicated because we do have one of these packages for each key derivation operation and for each key name. And then we can just like argue for a step by step and game steps over individual keys. And this will then end up being the functionality that we export. And the rest will be the simulator. So I introduced this concept of handle a bit informally already. So let's look at this in more detail. So handle is something that identifies a key. And we use this when you set a key. So when you first introduce a symmetric key that TLS allows, and also like a Diffie-Hellman key, we have them for key derivation. So if the adversary instructs this game to derive a key, it identifies the input keys by their handles. And the game or the key schedule then returns to the adversary a new identifier for this key that was computed. And this is the same for the other operations. And this is also how you access output keys in the end. And the structure, we're looking here at one of these operations is then like this. So it exactly encodes what you would, or what the adversary uses to call this key operation. So it's a bit string, and then it encodes the type of operation that we have. It encodes what key this is deriving, the input or the parent, and also additional arguments. And this is convenient, and it also closely, of course, models how this key is computed. So key computation essentially only uses information that is also present in the handlers. It just excludes the concrete secret values. And if we remember, like here, this handle that we use inside this is also of the same structure. So this is a recursive data structure, and it exactly tells us how we arrive at the output key from all this input key material without containing any secret information. So now I've talked a lot about what we do in this key schedule and key schedule security. Is this actually useful? And you want two properties. First of all, you want that this is actually provable for any interesting instances. And I'm telling you about our proof for TLS 1.3. So we do have key schedule security for TLS. And in follow-up work, there's also key schedule security for MLS, which is a new group messaging protocol. So we do have key schedule proofs for interesting protocol instances. What you also want, of course, is that this actually helps you to prove key exchange security. Otherwise, this whole work is kind of useless. And we also manage this. So there we have a proof that reduces key exchange security properties of TLS to the key schedule. And this will be on ePrint soon. This is then the picture of how you prove TLS security. And we skip the key exchange because this is not part of this rec. And look at the core part of the key schedule. And this is where this structure, this detailed structure of this game is really handy. And we need to first take a short look at expand security. So this is one of the security properties that we use in this proof. And this is, in a way, it's a PRF security. So the adversary sets a key, then calls evaluation on this expand function, which then stores the output keys here, and the adversary can access it. And the evaluation gets a key, runs a function, stores it. And important, of course, if we have a key that is supposed to be secret from the adversary can instruct keys to be sampled, but of course it cannot know the value. So instead, when the adversary instructs us to produce a new key, we produce a new random bit string. And here we have two variants. Also following, I think, standard modeling of like PRF security. So if this is a 0 up here, then we just store whatever the expand function will produce and provide this to the adversary. While if this is a 1, we also replace the output of this PRF by a random string or this expand function. So standard PRF security in a way, just written a bit differently. And then you have security requiring that the two are indistinguishable. So the one where you adversary that has access to the get, in one case gets the string as computed by expand, and in the other case gets a random string, random bit string. And we can now apply this to this picture. And remember that there's all stacks of packages here. So there's many extracts and expands and many keys. And then we can move things out a bit. And then we see this is the security assumption that we are looking at. And it's important we take one that has an already ideal. So on one key package up there, we can take everything else as a reduction and then just switch this output key via security assumption from storing the concrete value to just storing a random value. And then you can iterate this. So now you have another key package that was just storing real values and it's now storing random bit strings, and I can apply the security property again and again on different steps on this key schedule. Now this was, if this was all, this is very simple, but of course there's more to it. And one of the problems is redundancy that we have in this model. One of the sources of redundancy is Diffie-Hellman. So we do have this nice homomorphic property that like Diffie-Hellman of x to the alpha y is the same as the Diffie-Hellman value computed from x and y to the alpha. So if you take them plainly, we have different sources at deriving at the same value. And we want to prove uniqueness in the end, so we kind of need to argue about that. And let's take a look at what happens here in this model. So the adversary asks for computation of this Diffie-Hellman value. Diffie-Hellman package will compute the key and store this under this identifier, and then we confirm things back. And this is all okay, but assume that the second value was also stored. So there's a collision now. And the most intuitive way that you maybe think about it is just at this point, the key package notices there's a collision and then returns the value, the identifier of the value that it already knows. And we return this to the adversary. But of course, this is easily distinguishable. So we can't really use this argument. And we introduce here a translation. So the key actually returns the replaced value. and then the map returns to the adversary what it expects. And I mean, you can easily verify that this is computable at this step without access to the secrets at all. Now, of course, we don't want this for the output keys because we want to argue here that they are actually unique without any tricks. And the map here also doesn't go there. And this works via the restrictions we receive from the protocol. And if you look at here the key schedule, before these arrows go down, the key exchange protocol will include a transcript in this key derivation operation. So if I derive here a key, I will have included a transcript that contains the shares in this derivation operation, which creates distinct values. And therefore, we don't need to have this translation on output keys, and we arrive at uniqueness. Of course, this needs to be formally argued and as in a paper. And then you can just remove everything that is the map and left to it into a reduction and just care about the remaining key schedule that has this neat unique feature kind of automatically. Now, in our last step, this was what I said was like security assumption we used for this core proof. And I mean, you can describe security properties like this, but it's kind of inconvenient. We didn't even talk about what happens down here. So this is like security definition that has a lot of like unnecessary parts, and what you would much rather have is something like this. So a security definition where, on the one hand, in the real case, you just have an oracle that samples a random key, adversary submits inputs and gets evaluations out. And in the ideal case, the adversary always gets just random bit strings. And in the full version, we have a proof that actually we can reduce this security definition to the more standard formulation. Of course, there's some more complexity, as you can see. First of all, TLS, of course, allows algorithmic agility, so you can have different keys produced in different algorithms. And this one is just like one concrete algorithm, so we need to argue like for all choices of hash functions, and also we allow multiple source keys, whereas here we have exactly one key. So there are some more factors if you look at concrete security that is hidden in this formulation. And I'm through with it now. Yes. So yes. So that's it.
Thanks a lot. Other questions?
Hi, I'm Matilda. Thanks for your talk. I have a question actually about something you said in your video abstract. There you mentioned that a key takeaway from this analysis was that it would have been useful to extract from the Diffie-Hellman part before mixing, because you could have relied on less strong security assumptions. And I was wondering in particular if what you meant by this was that you could have, well, like you wouldn't have needed the Oracle Diffie-Hellman assumption. And also my second question is do you see any reason to keep it as it currently is, or should we just move to always extracting before mixing?
I think why it's this way is just like it saves another like key derivation operation, and people are kind of sensitive about how many of these you include. Also, it doesn't show in our slides so nicely, but it does, like the key schedule does have a regular structure that has like always one extract, two expands. And if you mix in, yeah. So there are, I think, non-cryptographic reasons to keep it in the way it is. And for security properties,
You rely on Oracle Diffie-Hellman.
we rely not just like on Oracle Diffie-Hellman, but we also have the salted Oracle Diffie-Hellman. I don't know if you if you've seen that part. So the adversary not only has like Oracle access to the Diffie-Hellman, but it also can choose the salt under which it's extracted. And that is kind of, yeah, you would like to not have that, at least from a cryptographic perspective.
And if you were to extract first, could you get around that entirely then?
Around the salted for sure. I'm not sure about. Yeah.
Thank you very much.
Any other questions? I've got one question. Your paper has, I just checked, more than 80 pages appendix. I mean, this is a great careful work, but what guarantees you that your proofs are correct? I'm 100% sure none of the reviewers read the full paper. I'm betting.
Also, we didn't submit what is now the full version, and I think there's also like we have a extended version and a full version of this paper online. It's quite annoying in a way. And yeah, 80 pages of appendix are too much, so to speak. I mean, one way around this, at least outsourcing part of verification of this proofs to like automated proof tools, and that would be super nice. We haven't done that at the moment. I mean, but something that we have in mind. Okay. And the other one is, I mean, like the last part I presented, you can just look at how this is the security properties are described and convince yourself that those are also reasonable descriptions. And then you save, I don't know, the 30 pages of the appendix already. So yeah.
Thanks a lot.
Repetitive and needs to be done.
I was hinting at if you're planning to formally verify this, because I think it's not human checkable eventually. Thanks a lot. I think then thank the speaker again. And then our next talk is online. It's YOLO Yoso, fast and simple encryption and secret sharing in the Yoso model by Ignacio Cascudo, Bernardo David, Lydia Gams, and Anders Kronring. And Ignacio is giving the talk.
Yes, can you hear me well?
Yes, I think they can improve the audio a bit.
Oh.
Try a different microphone.
I can try with the laptop one, but
now
much
it's
better.
Okay. I didn't do anything. So. Yeah. So thanks for the introduction, and I'm sorry that I cannot be there. But I hope that you are having a great conference. And yeah, this is the paper YOLO Yoso, fast and simple encryption and secret sharing in the Yoso model. And as the title suggests, this is about the Yoso model. This is a secure computation, secure multi-party computation model that is a little bit of an alternative to the traditional one. So in the traditional multi-party computation model, you have a fixed set of parties. The protocol proceeds by rounds, where at every round you have that, well, some parties can send messages to others and so on. In the Yoso model, you have instead a very large pool of parties, and then at every round, or each round is being executed by a small subset of these parties, by some committee. And the point here is that every party can be at most in one committee. And most importantly, the identity of the party is not known, or the identity of each party is not known until they speak. Essentially, the motivation for this model is that this makes corruption by adversaries hard. So because, well, basically the adversaries don't know which parties are going to speak until they do, and then when they do, then it's too late to corrupt them because, well, they have already spoken and they are not going to participate anymore in the protocol. So that's the motivation of this model. And but of course, in this model, we need to figure out how to implement the communication between parties, because in traditional MPC, well, you have that, well, parties are known, and so you can essentially assume that there are secure channels between each pair of parties, because you can instantiate that using public key encryption, like everyone will have a public key, and then, as I said, the identities of the parties are known, so you know which public keys to use in order to encrypt towards a given party. But in the Yoso model, the situation is a little bit different, because here you have that every round is run by some anonymous committee. So then the question is, how do you encrypt information towards a party that you actually don't know? And more generally, also, how do you, for example, secret share information among some committee that you still don't know? So there have been like several works dealing with this type of problem. And so the first one was this kind of public blockchain keep a secret by Benhamud et al. And there they were concerned about how to keep a secret shared during a long time in a blockchain. So by resharing it to different anonymous committees. And the sort of the appointment of these committees is a process that requires some bound on the corruption tolerance. So basically, you can at most have around 29% of the parties corrupted. Then this was fixed in this paper called Random Index Private Information Retrieval, where basically they could achieve any dishonest, any honest majority by a technique that basically allows parties to sample anonymous public keys from some list and then encrypt towards that those keys. Now the computational complexity of this is a little bit high. Later in this conference, there will be this presentation about this paper, Encryption to the Future. This is on Friday, and this approach consists in the following. So here we have that time is divided into slots that they are kept by a blockchain, and basically, when you want to encrypt information towards a certain party, what you are doing is actually encrypting towards a certain role in a certain slot of the of this time frame. So basically, you could be like encrypting towards the second row, the row number 2 in slot number 6, for example. And then there is a lottery that checks if the owner of a certain secret key will be assigned to that role. And if that is the case, then this party will be able to decrypt. So this is encryption to the future. You will see more about that on Friday. But also in that paper, there is like a weaker version called encryption to the current winner. And encryption to the current winner means that whenever you, at the time of encryption, the role is already assigned. So basically, the party that is going to be assigned this role is already like completely determined. And this is actually a simpler case, because while in the case of encryption to the future, the communication that you need in order to encrypt or to send an encryption of a message is linear in the number of total parties in the system. Here we will show that encryption to the current winner can be achieved with communication which is independent from the number of parties, or at least the online communication. Then there is a way of transforming this encryption to the current winner into full-blown encryption to the future using identity-based encryption. You can refer you to the other paper and to the other authors who know more about this than me. So in this paper, what we do is well, several things. So first of all, we suggest a solution for encryption to the current winner, as I mentioned, that uses shuffling, and well, where the ciphertext length is independent from the number of parties, as I said. And then we also looked into how to secret share information, and in a way that is compatible with this encryption to the current winner. And in particular, we come up with new publicly verifiable secret sharing schemes. And yeah, in particular, one of the proposals that we have is the most efficient that we know in terms of communication to date. It has a proof of sharing correctness whose length is independent from the number of parties. And this is interesting for also independent applications too, as I will mention. And then finally, we also have like, well, generalizations of these PVSs in order to also reshare information, not only share. I will explain a little bit more of that. So first of all, let me talk a little bit about the encryption to the current winner through shuffling. Essentially, the approach that we propose is very simple. So each party in the system will select a key pair anonymously, and then they will input their public keys into a mixnet, and the mixnet will essentially like shuffle these keys, and the resulting keys of resulting list of the public keys will be published in the blockchain. And this all can be done in a pre-processing step. And then once you have this list, then encryption to the current winner is essentially trivial because, well, a lottery will essentially select which public key corresponds to, or I mean, we'll select a random key in this list that has not been used yet. And then the party that needs to encrypt information will just use that public key to encrypt. So this is the solution for encryption to the current winner. We have actually a more elaborated strategy that even allows to preserve some anonymity after speaking. So basically what I mean by this is that you can encrypt or share information to a committee, and then have the property that parties can actually later on when they speak, that they can reveal that they belong to that committee, but not without revealing which of the parties of the committee they are actually associated to. So basically, which of the roles in that committee they were associated to. So this could be interesting. It doesn't really completely fit in this JOSO model, but we think it could be an interesting, I think maybe for some other applications. Now we think this is a good approach for encryption to the current winner, but when it comes to secret sharing, we need to also guarantee other properties. Like when we are secret sharing some value into a committee, then we also need to prove that what we are doing is actually a consistent sharing of information. So basically, for example, if we are using Shamir, we would like to prove that the shares that we are sending are actually evaluations of the polynomial of the right degree. So for that, we have the notion of publicly verifiable secret sharing, which was already introduced in the 90s. And this is simply a secret sharing scheme that has a publicly verifiable proof that the sharing that we are doing is correct. So basically what is going to happen is that we are going to send or we are going to publish shares in an encrypted form, and we are going to prove that the underlying plain text are a correct sharing of some secret. Now, this recently has had interesting applications, so most notably for the construction of distributed randomness generators or randomness beacons. But also it's an important property if we want to keep secrets in a blockchain for a long time, because if we are going to keep secrets being reshared in successive committees, well, we want to make sure that this is doing that actually there is some secrets being hidden by these shares. We want to prove the correctness of the sharing and then the resharings. Yeah, so in this paper we present two constructions of publicly verifiable secret sharing. One is a generic construction that well, is constructed from any homomorphic encryption scheme, well, or linearly homomorphic encryption scheme over a field, and then we propose this more efficient PVSS that is based on the well, DDH. The first one is based on this notion of well, linearly homomorphic encryption. Essentially, what we want here is that an encryption scheme where both plain text, randomness, and ciphertext spaces are linear spaces over some field. So, for example, they could be just groups of order P, where P is a prime, and that encryption is homomorphic in both the message and the randomness. This basically allows for simple proofs of knowledge of the plain text. And another thing that we want from this encryption scheme is that it has a proof of correct decryption. So we see two ways of having such a proof. One is that if the party that is decrypting can also recover randomness that can give you the ciphertext, then you can use the homomorphic property of the encryption in order to prove correct decryption. But also you don't need that if you also have decryption function which is linear in the secret key. In that case, you can also like construct proofs of correct decryption without needing to recover the randomness. So if you have this any of these properties, in particular, the second one is satisfied by El-Gamal. You can construct a publicly verifiable secret sharing scheme in the following way. So the dealer will share a secret using a linear secret sharing scheme, for example, Shamir. Then we'll publish the encryption of the shares under the public keys of the parties that are going to receive the shares. And then it's going to do the same thing, but now with a random sharing. So it's going to take some random secret, create a random sharing, and encrypt the shares, and yeah, publish those values. And now we can see this last thing as a first step of a Sigma protocol, and then we can essentially have a non-interactive zero knowledge proof by using just the standard trick of taking a challenge constructed from the public messages, and then opening a linear combination of the shares and the randomness. And then the verifier can check that the corresponding linear combination of the ciphertexts are actually the encryptions of these linear combinations that have been opened, and also that these values set i's that you have here are a correct sharing in the same linear secret sharing scheme. So this would be just the publicly verifiable secret sharing. And this is nice because it can fit with any encryption that we are using for our encryption to the current winner. This is secure if the encryption is actually in CPA. We also have in the paper some protocols to prove correct resharing and reconstruction of the secret. So essentially, resharing is a little bit more involved than proving correctness of sharing, because when you prove correctness of resharing, you need to prove that actually the secret that is underlying the encrypted shares that you are going to send is the share that you had before, for which the other parties only know a ciphertext. So you need to prove that, but you can do that from because of the linearity of the encryption scheme. And then if you can prove resharing, you can also prove correct reconstruction of a secret, because you can see reconstruction in fact as just resharing with a secret sharing scheme of threshold 0. Essentially, that would be like publishing your share of the secret, and then if everyone does that, then you can recover the secret. So that's the resharing reconstruction. And yeah, so finally we have this new secret sharing scheme that, as we say, is the first publicly verifiable secret sharing scheme that has a constant size overhead, meaning that the size of the proofs that we are sending of correct sharing are independent, or their length is independent from the number of shares. And this, as I say, can be interesting for other applications like randomness beacons. Here in this case, the secret is an element of some cyclic group of prime order, where the DDH is hard, and the dealer will publish as shares an encryption that is one element in the group, and as correctness proof just 2 elements in the field of size P. And the ideas that we have, that we combine in order to have this scheme, are essentially 2. So one is that while in previous publicly verifiable secret sharing schemes, we had that share receivers would have key pairs for the discrete log. In this new scheme, then the dealer will also have a key pair. That's the sort of novelty that we had seen in some constructions for Palier, so for secret sharing scheme based on Palier, but not in the case of the discrete log. And then in order to prove or in order to share an element of the group, what you do is to basically Shamir share the discrete log, but you actually don't need to know this discrete log. So because you can just essentially construct a sharing of 0 and then add that to the secret that you have. So the idea would be just to sample a polynomial that's well, like here it should say 0 actually. That's such that the evaluation of this polynomial in 0 is 0, and then you will add that to the element of the group. And then in order to encrypt this share, you add the element. This should be a pk sub I. So essentially, you are one-time padding your share with the Diffie-Hellman key that you would get between the dealer and the ith receiver. So this should be PKI here. This is one idea, to give the dealer a key pair, and the other idea is to use this scrape check that we had in a paper 5 years ago. The idea is that in order to test that something is a correct sharing in Shamir's scheme, you can notice that the set of all correct sharings is a linear code, so it has a dual code. And whenever you have a vector of n elements, in order to have a test, so that to see that it is a correct sharing, you could sample an element from at random from the dual code, and take the inner product. If that inner product is 0, or let's say if this the vector C is in the code, then the inner product will always be 0. If it's not in the code, then it will be 0 with very small probability. So if we port that to groups, then now we have a vector of n elements in the group, and we can test whether those n elements are a Shamir sharing, so meaning of the form f of I times the generator with the polynomial of the right degree, by just taking this linear combination and seeing if that is 0. So that's the other trick. So the construction in the end that we have is the following. So we have that the dealer and the share receivers have all keys, key pairs. The dealer constructs the shares for the secret, then encrypts these shares, sends these encryptions. The ith party can actually recover the ith share. And now the proof consists in the following. You sample via, well, sort of a Fiat-Shamir technique, some random code word in the dual. You take the linear combination with coordinates being the components of that code word. And now the point is that this factor here should go to 0 if the sharing is a correct one. And then you get an expression where essentially the linear combinations that you have in left and right are public elements that can be publicly computed, and they are related by the secret key of the dealer. But now the dealer only needs to prove that her public key is constructed, or essentially the discrete log of the public key with respect to the generator is the same as the discrete log of this V here in base U. And that is enough. This is a very standard non-interactive proof that only requires 2 elements in the field. And so we have this construction finally that only has 2 elements of the field as a proof of correctness. As remarks, we have proofs in the paper for correct resharing too for this scheme. And one problem of this construction is that parties can only reconstruct a group element and not the discrete log or the exponent of the element, which is not really nice for MPC. So we think that to fix that, we could use the scheme of Castaños Leguilamy. I think that there is a talk in this conference also based on this work, but essentially the work consists on, or the encryption scheme requires some group with hard DDH that has an easy, or a subgroup with an easy discrete log, and that allows to reconstruct the exponent there. So as a conclusion, then we propose efficient encryption and publicly verifiable secret sharing for a current winner in the context of YOSO model. And in particular, we have this new PVSS that is the most communication efficient that we know to date, and can be interesting for other applications such as construction of randomness beacons. And as a future work, we would like to have constructions that allows us to parties to reconstruct not only group elements, but also like the associated field elements, so that we can use it more efficiently or use it for MPC. Yeah, so that's all. Thank you.
Thanks a lot for the talk. That took a bit longer, so we switch immediately to the next talk, and we'll have to take questions offline. The last talk of the session is State Machine Replication under Changing Network Conditions by Andrea Alexandru, Erika Blum, Jonathan Katz, and Julian Loss. And Erika will give the talk, I think.
Yes, hello everyone. Let me just quickly get this screen sharing up and working, and video. Hopefully everyone is now seeing a presentation as they expect. Yes. Okay, excellent. So thank you for the introduction. Without further ado, I'm excited to talk to you today about some of our recent work on reaching agreement in unknown or changing network conditions. This is a joint work, as was just said, with my co-authors Andrea Alexandru, Jonathan Katz, and Julian Loss. So I'll start with a quick overview of the core problem, state machine replication. A state machine replication, or SMR protocol, allows a set of parties to agree on a growing ordered log of transactions. Individual parties receive unordered inputs and need to agree as a group on an ordered sequence of outputs. In practice, these outputs are often batched, so we'll think of parties' logs as sequences or arrays of these batches, which we'll call blocks. The key challenge here is that some of the parties might be faulty or Byzantine, which means that they might deviate arbitrarily from the protocol. And for an SMR protocol to be secure, we require that all honest parties agree on the sequence of blocks that were output and the transactions in those blocks, even if the faulty parties are being coordinated by some single mastermind adversary. We can view SMR as one of several problems under the broader umbrella of consensus problems. Another problem under that umbrella is Byzantine agreement, where parties agree on a single value. If it helps for the purposes of this talk, you can think of Byzantine agreement as single-shot agreement on binary values, and SMR as multi-shot agreement on arbitrary values. SMR as a problem has a long history in distributed computing, and recently it's received special attention because it turns out to be a useful abstraction for blockchain protocols. Under the hood, many blockchain protocols use some form of a consensus protocol in order to order transactions as they enter the network. I say many and not all because people call lots of things blockchains, and I'm sure somewhere out there there's a thing that someone is calling a blockchain that does something completely different. But in this talk, we'll just make our lives easier and all agree to treat blockchain and SMR as the same thing. So that's the big picture. In a little more detail, here are the properties that we want from an SMR protocol. Throughout, we'll let N be the total number of parties and let T denote the number of faulty or Byzantine parties. So the first property that we require is consistency, which means that all parties who have output the kth block agree on what's in that kth block. The second property is completeness, which says that every honest party eventually outputs a block at all indices. Essentially, this is just saying that the protocol can't stall forever. Eventually, as long as you keep working, you'll eventually have something to put at every index. Next, we have a property liveness, which says that if a transaction is input to sufficiently many honest parties, sufficiently many here being at least N minus T of them, then all honest parties eventually place that transaction somewhere in some block. And finally, the last property that we'll consider is external verifiability, which means that given some public parameters and some additional information, anyone, even someone who was not participating in the protocol but was observing, or maybe even someone who was completely offline and just woke up all of a sudden after the protocol, can verify that a block was honestly output and that it was output at that particular spot in the array. And furthermore, we require that dishonest parties can't generate a valid proof for a block that wasn't actually output by the honest parties. So a quick caveat, there are lots of different variations on this definition, but for our purposes, we'll say that an SMR protocol needs to meet all 4 of these properties. So state machine replication protocols and consensus protocols as a whole have been studied in a wide variety of network synchrony models. And here on the slide, you'll see 2 extremes. On your left, we have the synchronous model, where we assume that there are that each party has synchronized clocks and messages arrive after at most some fixed delay, usually denoted by symbol delta. And under this model, assuming public key infrastructure, it's known that state machine replication is feasible if and only if there are fewer than n/2 corruptions. At the other extreme, in terms of network models, we have the asynchronous model, where there are no synchronized clocks and messages can be arbitrarily delayed. In the asynchronous model, again, assuming public key infrastructure, the optimal corruption threshold is n/3. There's also the partially synchronous network and many other flavors of in-between models, but they won't be relevant to this talk. So in this paper, we consider what's called the network agnostic model, where the network might be either synchronous or asynchronous. It's parameterized by thresholds TS and TA, so that if the network is synchronous, we allow the adversary to control TS parties, and if the network is asynchronous, the adversary gets to control TA parties. And what we want is to design a single protocol that just works, even if the honest parties don't know which mode they're in during a particular execution. So this is a model that was introduced in an earlier work by myself and some other co-authors, and has been since then extended in a couple different ways. And one of the key questions that we address in this work is how can we improve the communication complexity of network agnostic SMR to match the complexity of similar fully asynchronous protocols. Oh, and just as a last note, almost forgot, one of the results in these prior works that we'll refer back to a few times is the fact that consensus in general and state machine replication specifically is feasible in this model if and only if 2TS plus TA is less than n. So just to help us gain some familiarity with this model, I like to think of it as sort of an informal cryptographic game between the adversary and an environment who plays on behalf of the honest parties. For simplicity, I'll describe this with static corruptions, but you can also consider adaptive corruptions, and we'll get to that shortly. So in this game, the adversary has a switch, and before the start of the protocol, they secretly choose one of these 2 modes that we've allowed them. Either there's the synchronous network with a higher number of corruptions, or there's the asynchronous network with a lower number of corruptions. So before the protocol even starts, the adversary picks whichever setting they want. And since we're in the static world, a set of parties that they want to corrupt. Let's say that they choose the asynchronous network. So they tell the environment, these are my choices for this execution, and then they just run the protocol as normal. Our security definition requires that the adversary can't break security, even if the honest parties don't know which mode they're in. So that's the network agnostic model, which is actually the first of 2 models that we're going to talk about in this talk. The second model is new in this work and adds a new twist on the original network agnostic model. So remember that in the network agnostic model, the adversary is allowed to choose the underlying mode exactly once before the start of the protocol. They have to commit to it. And a natural next question is, what can we hope to achieve in a model where the adversary can switch back and forth between these nodes during the lifetime of the protocol? Maybe we have some pattern where it's switching back and forth. And we found that it's not at all trivial to translate the results from what I'll call the original flavor network agnostic model to this new model. And to see one of the reasons why, here's a simple example. Suppose the network is initially in the synchronous mode and the adversary has control of the higher number of parties, TS, where TS is allowed to be greater than n/3. If the network becomes asynchronous, while the adversary still controls those parties, there's nothing that we can do that will preserve security. And we know this because there's a classical impossibility result that says consensus is impossible for greater than n/3 corruptions in the asynchronous model. So that's a lost cause. And so to get around this impossibility result, we need to assume somehow, we need to bake into our model that the corruption capability of the adversary also decreases whenever it flips that switch to asynchronous. So we'll get into the details more later, but essentially in this flavor, in this new exciting flavor of our model, we assume that parties have a capability that allows them to periodically reboot and kick out the adversary. But this has a notable complication that this doesn't remove the secret state that those parties had from the view of the adversary. So even if an honest party has, say, rebooted their computer and reloaded from safe state so that the adversary is no longer in control of the machine, any secret keys and anything that was lying around while the adversary was in that machine are still compromised. And so we'll need to deal with that. So again, to sort of get a little bit of fluency with this new model, let's look at our informal cryptographic game. So like before, the adversary has this switch that lets them determine the mode, but now we're going to allow them to sort of adaptively choose that setting and their corruptions over the course of the game, however they like, as long as at each point they're obeying this corruption threshold. And again, I'm sort of deliberately glossing over some of the details, but we're assuming here that periodically parties are caused by the protocol to refresh booting out the adversary, and then the adversary gets to make further choices about who to corrupt. More on all that later. So here's just a brief overview of some of the most related work. There is a really wide and deep body of work on this topic, so I'll limit our view to just sort of the most closely related. So if we look at the state of the art in fully asynchronous protocols, which are sort of our reference point here, we see that in both the static and adaptive adversary models, we know of prior work by these authors I've listed at left that gives us cubic complexity for batches of n transactions. So that's going to be our goal, or the bar that we've set. And then if we take a look down at these bottom two rows, you'll see these results that I mentioned briefly from prior work, where we had these network agnostic SMR protocols that unfortunately fell a little short of that bar. You'll see that in particular, tardigrade, which is our adaptively secure protocol, had n⁴ communication complexity per batch of n transactions, which could be better. And then you'll see upgrade, our second protocol, achieves security against a static adversary and does a little better, amortized linear cost, or cubic per batch of n² transactions. But batches of n² transactions are quite large and aren't going to be suitable for all use cases. So we'd like to do a little bit better if we can. So that brings us to this work, where we consider not only the network agnostic world, but also this sort of arbitrarily changing network world that I've just mentioned. And we're going to present two protocols, update and upstate, where update is our adaptively secure protocol that gives us cubic complexity for batches of n transactions. And then we're going to briefly talk about upstate, which is a static version with that nice linear, this time for batches of n transactions. And the cost that we pay, sort of as before, is this almost optimal corruption threshold, which is an open question to resolve. So let me quickly walk us through sort of the roadmap of the rest of the talk. We're going to look at our adaptively secure protocol, update, which has the quadratic amortized communication. We'll follow that with a quick look at upstate, which is our statically secure SMR protocol with linear amortized communication. Then we're going to take a bit of a detour and start working in this new flavor of network agnostic model that I mentioned. And then finally, and that will take us by way of a folklore impossibility result of purely asynchronous proactive secret sharing with refresh. And that will motivate a slight relaxation or a slight constraint that we place on the adversary in order to get sort of the second best option or the next best thing, which is state machine replication under those adaptive networks changes, but with a slightly constrained version of a mobile adversary. And then finally, I'll wrap up by just mentioning a couple open problems. So we are here. We've got some work to do, I see, looking at my clock. So I guess we'll get moving. So just to quickly look at some model and terminology that we'll need. Again, we have Byzantine faults where it's bimodal or binary depending on the state of the network or the mode that the network is in. And TS and TA can be anything you like as long as 2TS plus TA is less than N. And we at times consider either alternatively adaptive or static adversary. So we have atomic send operations, which you don't need to think too much about, other than it just means the adversary can't corrupt in the middle of a multi-send. And then we're also throughout going to assume that the parties have access to a public key infrastructure, in particular for a threshold signature scheme and threshold encryption scheme set up by some trusted dealer. And this is going to take us through our protocol's update and upstate. Okay, so our basic recipe for update will look a bit familiar to those of you who are familiar with Honey Badger BFT and related protocols, and might look very familiar to any of you who may have somehow or another seen tardigrade, our protocol from prior work. So each party starts an epoch at a fixed local time. And the first thing that they do is they take their buffer and they're going to choose a random assortment of things in their buffer and threshold encrypt them. And the reason for this is essentially just so that the specific transactions chosen by each party are hidden until the very end, all the way at right where you see decryption. We want to just hide the details of which transactions were or weren't chosen until the last possible second when the output has already been determined. That just sort of limits an adversary's ability to manipulate whose transactions are or aren't getting included. This is a relatively standard known technique in the literature. So the next thing that happens is that parties sort of take these samples that they've encrypted and spread them around to all of their friends, multicast them, and assemble them into what we call pre-blocks, which is just sort of a fancy word for an intermediate value of a bunch of people's inputs. That then gets put into sort of our first major building block, which is called block agreement. I'm not going to get into all the details of that here, but I'll refer you to our previous paper where we present tardigrade for the details of that protocol. Essentially, if you like, you can think of it as a form of multi-valued Byzantine agreement, but for our purposes, it's just sort of the synchronous building block. It doesn't necessarily do anything if the network is asynchronous, but it works very well if all of the parties, if the network happens to be synchronous. So let's see. And then sort of our second major building block is this asynchronous common subset building block, which we do a slight tweak or modification to sort of the standard recipe that uses error correcting codes. I think that's a pretty neat detail that I encourage you to check out in the paper if you have the time. And so the main idea here is that whereas the block agreement is the hero in the synchronous network, the asynchronous common subset, as you might guess from the name, is the hero if the network happens to be asynchronous. And in either case, in either setting, without knowing which setting we're in, one of them is going to do the heavy lifting and the other one just has to stay out of the way, essentially. So I'll move through these in the interest of time. So this is the main idea behind our network agnostic SMR protocol with better efficiency. And we can get even better efficiency versus static adversary by using a fairly common trick in the literature, which is to use techniques to reduce the communication complexity, or sorry, use committees to reduce the communication complexity at the cost of an epsilon factor loss in the corruption threshold. Okay, so we are here, and as I said, I have some more work to do. So as I sort of alluded to earlier, this model where there's a fixed network mode throughout the whole lifetime of the protocol is a bit unsatisfying, especially when we think about a state machine replication protocol that's going to run for a large number of epochs. And this motivates considering a mobile adversary. So what we're going to do in order to accommodate that mobile adversary is assume that there is some code in untamperable memory that restarts and forcibly flushes out the adversary. Because essentially, if we don't have something like this in our model, we're kind of stuck, because if we're ever in the synchronous setting and the adversary corrupts more than the n/3 number of parties, which is sort of an important and interesting part of our model and part of this problem, then if the network ever in the future switches back to asynchronous, we know that we run into that hard barrier, that impossibility result I mentioned earlier. So somehow our model needs to include this reboot in order for us to get anywhere. So is that enough? Say if enough parties flush out the adversary before a network change from synchronous to asynchronous, does that just give us security? And unfortunately, the answer is no, because rebooting doesn't erase a rebooted party's internal state from the adversary's view. And so without somehow refreshing that internal state, bootstrapping the party who was corrupted back into the protocol, that rebooted party is going to remain passively corrupted or exposed. So the protocol uses threshold schemes. As we mentioned, the protocol uses threshold schemes. And so in particular, the problem is that the adversary can just continue hopping between parties and never corrupting more than the allowed number of parties at any given time, but it sort of just keeps collecting keys until it has enough to cause problems. And so we're going to need to deal with that if we want any sort of interesting, non-trivial result. And along the way to finding this sort of sensible relaxation, we proved this folklore result, the impossibility of asynchronous proactive secret sharing with refresh. It turns out to be very, very sensitive to the exact definition of what you mean by asynchronous proactive secret sharing with refresh. And so I won't get into all of that here, but I think it is a neat thing to see formally done out. And so I encourage you to look at that in the paper if you're interested. And that impossibility then translates directly to network agnostic. So again, just the takeaway here is we can't get sort of that nice natural definition of security that we would want. And so that motivates this relaxation that I'm about to tell you about. And the key relaxation here is we consider a limited mobile adversary where they can only hop around within a set of at most TS parties. So it's sort of like initially they can hop to whoever they want, but eventually they've sort of determined that set, or they've boxed themselves into that set. And so this is more general or more powerful than we originally considered. But as we said, we can't really hope to get anywhere against a fully mobile adversary. And we found that this is sort of an interesting non-trivial relaxation. The rest of the details of the model are largely the same, except for that reboot capability. Yeah, and so it turns out that we really only need minor changes to the protocol that I already showed you in order to get this nice new definition of security. The main ideas, just say really quickly, are to use an asynchronous Byzantine agreement as a building block with a higher internal threshold. For example, here's one in the literature that also happens to be our prior work. And then finally, we use a modified ACS with error correcting codes that help us sort of get around the fact that we might have fewer shares to reconstruct than we would otherwise hope. So finally, I'll just leave these up because I think I am properly out of time now. Thank you very much. Here's the link to our paper. Questions, comments, compliments, and complaints can be directed to my email, which is here on your screen. So thank you very much. I'll wrap it up there.
Thanks a lot. We actually would have time for a quick question if someone has one. I don't see any, then thanks a lot. And the general chairs have an announcement.
Yeah, we regret to announce that Mr. Edward Hauk has tested positive. What does this mean to you? Basically nothing, unless you've been in close contact with him.